Good afternoon, everybody. This is Steve Doubleday, and I'm talking to you remotely today from the East Coast, and I'll explain why shortly. But today I'm going to give an update on my dissertation topic, a computational model of simulation. And we'll start out with a demo of the work I've done this past year, and then we'll come back and talk about what's next. So we're going to pause here for this demo, and then I'll be back shortly. And we're back. Okay, the demo we've just seen is about XNets, and this will have an important place in the model I hope to generate here of simulation in rats. So the hippocampus of rats and approximately all mammals represents places the animal's been through in the environment. And particularly in rats and mice, we've been able to see that individual cells can be recorded, and we can see that they respond very specifically to particular places that the animal knows in the environment. Not only that, particularly during quiet periods, but not just during quiet periods, also during a couple different types of sleep, we can see very rapid sequences of these place cells kind of lighting up, representing either what appear to be trajectories in the past or possibly trajectories in the future. Trajectories in the past get called replay, and those in the future get called pre-play. A really clear version of this was found by Pfeiffer and Foster in a 2013 paper I've discussed in some previous presentations, and we're taking that as possible evidence of the animal actually simulating motion and generating these trajectories. Let's take a look at what that might look like. Let's do a demo of a rat in this arena. So to orient you, first off, this is an open arena, about 2 meters on a side. There are 6 wells in both directions, each of which can have a reward in it. The blue dot, sort of towards the middle, is randomly placed, and it's the home location. So for a given day, for all the trials on a given day, the rat will start at the home location, but from day to day, that home location will move somewhere else. So there's nothing magical about it. It's just home for today. The task for the rat is to start at home and find randomly another location that has a reward in it. And in this particular case, it's the green well towards the upper right. So the rat, depicted by this cartoon over here on the left, is moving around the arena. The cartoon is generated from a video image of where the rat was physically moving. The sort of funny yellow marking there to the upper right of the rat is what cells in its hippocampus are predicting is its actual location. And you'll notice as the rat moves that these yellow, red, white kinds of firings depicting the energy level of these cells track his physical location really closely. So let's go have him find his first reward. So this is approximately real time, and rat's moving around. You can see that his hippocampus is tracking his physical location very well, and he's homing in on his reward. Okay, so let's pause it there for a second. At this reward location, we're going to now see, particularly while he's quiet, enjoying his food, we'll see very rapid. They're slowed down for this demo, but they're 15 to 20 times faster than his actual physical movement. We'll see sequences of cells lighting up, usually moving away from the animal, and they look like paths through space. We'll see several of these, and the last one will then be followed by the rat's next motion. The structure of the experiment is such that once he finds his reward at the random away from home location, that magically there will be another reward that appears at home. So it's to the rat's advantage to remember where home is and to head back home as soon as he's found this first reward. Home is only rewarding once he's found the away location. So there's no automatic reward for any given location. It's only once you've followed the temporal pattern of I leave home to go away, and then once I'm away I got to go back home. So let's watch this piece. Here are some trajectories. There's one. Here's another. And that's heading, notice it crossed the home location. And now we follow his actual behavior and he heads for home. Okay. So that's the behavior that we're hoping to account for in this model. And I'm currently thinking in terms of 4 components in the model. In the upper left is the neocortex. In the upper right, we have the place system, which is roughly the hippocampus. The lower left is the path integration system, which figures out how to do the geometry of moving through an environment. And that's at least the medial entorhinal cortex. And the lower right are the motor routines that that we're either generating actual motion or sometimes simulated motion, and we're implementing those as the XNets I demoed previously. So the path of logic here might very roughly be the neocortex comes up with a target location that looks promising. The path integration system figures out what heading and distance would take us there, passes that off to the motor routines, which in this case, in the simulated environment, execute without sending commands to the motor neuron, so the rat doesn't actually move but is thinking of moving. And every time it takes a step, the steps it's taken and the speed it's moving at get passed back to the path integration system, which calculates through a set of fields called the grid cells, which are a sort of geometric overlay to the current environment, where it physically is on that path it had previously calculated. And those grid cells then activate the corresponding places back in the place system in the hippocampus, and that generates the trajectory that we see in the experiment. And those trajectories get forwarded over to the neocortex. The story I'm proposing here is that the neocortex is updated slowly. It's a set of neural networks whose weights have to be modified slowly for it to learn effectively, and that having all of these simulated trajectories come in gives the neocortex a chance to learn much more quickly than the rat could through purely physical motion what the outcome is of a given trajectory. So we send many trajectories through, and the neocortex learns faster to pick up the pattern in the experiment and to figure out this temporal ordering. We got to leave home in order to come back to home after we found a reward somewhere else. So that's the model in a nutshell. Let's talk about this HTM component, this neocortex component, because that's where I'm shifting my attention now. Jeff Hawkins in 2004 proposed a model of cortical processing as regions arranged in a hierarchy, and he implemented this in software, in open source software called Hierarchical Temporal Memory. So regions talk within themselves, and they get inputs from lower in the hierarchy, and they provide feedback back down from higher levels back down the hierarchy. In a given region, we model a layer of cells, which are a simplified version of a neuron, Cell activation generates a sparse representation of the input, which is an efficient way to represent things in a neural network. And we get neighboring cells predicting a cell's activation in the next period of time, which is then matched against what actually comes in, and we generate an inference as to whether what's happening is what we expected or not what we expected. And if it's not what we expected, we forward it to a region higher in the hierarchy, which attempts to make sense of it, and that pattern happens over and over again until we generate a stable representation of the problem. So that's the HTM software component that models cortical learning. Next for me is actually later on this evening, I'm spending time with my new granddaughter. My wife and I are visiting my son and his wife in Connecticut, and then I'm spending the weekend in New York on a semi-annual hackathon that that Hawkins and his company Numenta hold to bring new and sort of intermediate programmers up to speed on this HTM software. So I'm going to attempt to figure out by the end of the weekend whether HTM can successfully capture the temporal pattern that our rat has to learn in the Pfeiffer and Foster experiment. So that's the goal for the weekend, and then the goal for the summer is to do an awful lot of reading. So that's my update. With any luck, I'm on the phone and can answer questions. Thank you very much.